So I want to talk about anti-differentiation, and we want to build off of what we looked at in the activity yesterday, looking at area under the curve. And when you do the problems dealing with the left and right hand rectangles, really what you're doing is you are finding or approximating an integral. Okay? You're approximating an integral. And I want to show you really what's going on. This upper and lower rectangle idea. Also left and right, you'll see them written as. The upper and lower and left and right, how those are paired, will depend on how the function is drawn. Okay, so you can see here. Let me switch to that. You can see here the function is increasing. Okay, so when I draw the upper rectangles, what that means is that the rectangle will be hitting the function on the higher side, and inevitably what ends up happening then is that I have a little bit too much. Okay, so that part of the area, if I were to approximate the area from 1 to 4 of x squared plus 1, I'd get a little too much there. And then here, upper rectangle, I draw a rectangle to the higher side. Okay, I have a little too much here. And then, of course, here at 4, I'm going to the higher side again. I'm getting too much there. So we're getting too much area. That's why this is an approximation. Now, if I'm finding this approximation, notice I'm using rectangles that are all the same width. Okay, these are all a width of 1. So it's 1, it is 1 times 5, because 5 is the height of that rectangle, plus 1 times 10, plus 1 times 17. Okay, so 5 plus 10 plus 17 is 32. So this is approximately 32 square units. Okay, now in this case the upper rectangles happen to be the right side, or the right rectangles. Okay? Now, we can also do lower rectangles, which if the function is increasing, the lower will be the left-hand side. Okay? Now, if this function were decreasing, those would be switched. Alright, so you have to look, if it says upper and lower, you have to look at whether those are left or right, depending on whether the function's increasing or decreasing. Here, if we're doing with the lower rectangles, you can see, because it's increasing, it's going to hit it on the left-hand side. So this first rectangle is 1 times 2. And the second rectangle is 1 times 5. And the third rectangle is 1 times 10. So here we have an approximation of 2 plus 5 plus 10, 17 square units. Okay? And you'll notice, obviously you can see here, we're missing some. Okay? This is too little. Okay? Alright, so we have too much, we have too little. How could we get a better approximation? Average these two, okay? If I were to average these two, then I'll get a better approximation, okay? So, if I do 32 plus 17 divided by 2, that's 49 divided by 2, which is 24 and a half, okay? 24.5. So that would be the average. Now that's still an approximation, but it's going to be closer than either the upper or the lower rectangles is. Now the nice thing is that SL does not make a huge deal of this. Let me show you, though, what we're working with, and then we'll take a step back up to the top and see exactly what we're doing here, okay? In AP, we would spend several weeks dealing with what are known as Riemann sums, okay? Riemann sums. And what we have here is, what we're finding is the integral. Now, up here you can see we have the term definite integral of a function from a to b. So what we've done is we've defined this interval, a to b, and we want to find the area under the curve. And when we say area under the curve, we're really talking about the area between the curve and the x-axis. Okay, so it cuts it off at the x-axis, and the curve cuts it off here. So we're finding this area right here. And you'll see the notation for this is right here. This is notation that you should be very familiar with, okay? Now, just to break down this notation, this symbol here, it's a stretched out S. That's our integration symbol, okay? A here is the lower bound, B is the upper bound. You put the function in here, and then this D is what's known as the differential, okay? That differential represents the width of the rectangles, okay? It's representing the width of the rectangles. Now, I don't want to get too far into the Riemann sums, but I think it's helpful for you guys to see this. What we're doing here, when we do the integral from a to b of f of x dx, you notice how up here we were taking the width of the rectangle and multiplying it by the height of the rectangle, right? Mm-hmm. If I wanted to still use lower rectangles, how could I get a better approximation? Add more rectangles, yeah. Check this out. If I were to take this, and let's say I cut these into rectangles that were half a unit wide. So you have that, and then you have that, you have this, and you have this, you have this rectangle, and you have this rectangle. Notice the amount that I'm missing out on has shrunken. I'm missing out on that piece, and that piece, and that piece, and that piece still.
How do you tell how tall the one on the right side? Like, because they're in the middle of...
Well, they're just going straight across from where we hit the function on the left, because they're rectangular. Okay? So if this rectangle is this tall, it's just going to go straight across. And I've got a rectangle there.
What about the taller one that goes...
Okay. Well, this one, it just goes up until we hit the until we hit the function, and then it cuts straight across until we get to 4.
Okay, so we don't need to find the y.
Well, no, if we were doing this, we would have to find all those y coordinates. We'd find it at 1.5, 2.5, 3.5, and we'd do the areas 1/2 times whatever that equals, 1.5 times whatever that equals, and add up this time 6 rectangles instead of just 3. But notice that would give us a better approximation. What the Riemann sum does is it actually takes this and it says, well, wait a sec, what if we get a better approximation by doing more rectangles?
Can we get a limit?
We are going to get a limit, okay? We're actually going to take, and this is what the integral is giving us. It's the limit as the number of rectangles approaches infinity. Okay? Okay, so what are we taking the limit of? We're taking the limit of the sum of the areas of the rectangles. The sum from I equals 1 to n. Okay, and thankfully, you guys will be thankful to know you aren't going to have to do integrals this way. In AP, we spend a couple weeks doing them this way, and it's a real pain. Okay, but here we go. So what we have here is a rectangle, right? Well, the rectangle is the width of the whole interval, which is b minus a, divided by the number of rectangles, right? So if it's, in this case, it's from 1 to 4, so that's 3 units wide. If I have 3 rectangles, then it's going to be 3 divided by 3. Each one is 1 unit wide. Okay? So I have b minus a divided by n. The width of the interval divided by the number of rectangles. Okay? That's the width of the rectangle. Then we multiply that by the height. Okay? Well, the height is going to be the function evaluated at a plus, I drew this too close, a plus I times b minus a over n. Okay? And notice what we're doing here is we are adding the width each rectangle. Now this one would be actually for the right rectangles. If I want to do the left rectangles, instead of an I would plug in an I minus 1. Okay? But again, the nice thing for you guys is that you don't have to do this. But I want you to see it because it's helpful in understanding what we're really doing here. Okay? These aren't just some arbitrary rules that someone just made up. Okay? This is the result of a lot of thought and trial and error and what if. Okay? And discovery like this is messy. Okay? And then someone figures it out, and then someone else builds on that and refines the process, and that's how we get these nice, much simpler formulas. I know that doesn't look simple, but it didn't start out looking that pretty. Much simpler formulas like this. And then we start doing this process, and we start recognizing patterns, and we say, oh, there's a rule that we can make. Okay? So that's what we're doing, though, when we're finding these integrals. The integral from a to b of f of x dx. Okay? And because we take the limit as n approaches infinity, we can actually find the exact area. We're no longer approximating. We can find the exact area. Okay? So, let's build off of this and actually look at using some stuff. Okay? Let's first of all talk about when we are taking the integral, okay? When we are taking the integral, what we're doing is we're starting with the derivative and we're finding what the original function was. These are kind of inverse operations, okay? As you'll see here, they're not exactly inverses of each other, but they're kind of inverses. Because taking y and finding dy dx was called differentiation, we call this anti-differentiation, opposite or against differentiation. Alright, that's why this big old term exists. It's anti-differentiation. So, if you're starting with the function, you're finding the derivative, that's differentiation. If you're starting with this and you're trying to find what the original function was, that's anti-differentiation or integration. And a common way that we denote this, because usually they don't say here's f prime, they'll just say here's f, and then you've got to take the integral of that. We use a capital F. Okay? Capital F is a function where its derivative equals the function f of x. Okay? So the derivative of capital F of x is f of x, and the antiderivative of f of x is capital F of x. That notation is important to understand, especially as we look at how to evaluate definite integrals, okay? We're not going to get to evaluating definite integrals today, but we're going to build to that. The first thing that we need to focus on is how do we get what this capital F of x is, all right? So, I want you to think about this in terms of these functions here. Okay, let's start with x cubed. All right, I want you to think, we want to try to find the antiderivative of x cubed. So let's think about this. The derivative of what equals x cubed? So what are you thinking here?
1/4x to the 4th. Or don't you like
Okay.
add 1 and then put it over what's in front?
Well, why are you adding 1? Because we want to end up with x cubed.
Yes, because when you find the derivative, you have to subtract 1, so you have to add 1.
Okay.
And then put it over that because you have to multiply it by the front.
Okay, think about your power rule for taking the derivative. When you take the derivative of something, of a polynomial like this, you lower the power by 1. So I must be taking the derivative of x to the 4th, right? But if I take the derivative of x to the 4th, I get a 4x cubed, not an x cubed.
So it has to be over 4 because you have to divide it.
So yeah, so if I throw in a 1/4 times that x to the 4th, then I'll have 1/4 times 4x cubed, and that will equal x cubed. So here's what we can say. I'm going to use the notation for the integral. The integral of x cubed dx. Notice I'm not putting bounds on it. I'm just going to find the antiderivative. The integral of x cubed dx is x to the 4th times 1/4. Or you could say 1/4 x to the 4th or x to the 4th over 4.
Don't we have to do a capital F?
Okay? So, that notation, what you're talking about, if f of x equals x cubed, that means capital F of x is x to the 4th over 4. Okay? Does that make sense? All right? Let's try to think through b here, e to the 2x. Okay? E to the 2x. So the derivative of what would equal e to the 2x?
Ooh. Well,
2e to the 2x.
Okay?
no.
Wait, 1 over 2.
1/2 e to the 2.
E to 2x over 2.
Okay, let's try it. The derivative of e to the 2x would equal what?
Or
2
Chen-Yang.
2e
Come on, dude, stay with me.
2x.
Okay?
2e to the 2x, right?
Okay, yeah, if I took the derivative of e to the 2x, I would get 2e to the 2x. Okay, how do I get rid of the 2? I throw in a times 1/2 here. So times 1/2, okay? And that cancels out, and that leaves me with just e to the 2x, okay? So we could say then here, the integral of e to the 2x dx equals 1/2 e to the 2x. Okay?
So do you just write the dx there? Is that just something that you do when you're notating it?
Well, okay, think back to, remember the Riemann sums? You know how we did f of a plus that mess
Yeah.
times b minus a over n?
The b minus a over n is the dx.
What we were doing is height times width,
Okay.
okay? So the height is that f of whatever. That's the e to the 2x part.
So
The dx is the width of that rectangle. So that b minus a over n, when we take the limit, that b minus a over n is called the differential. So that's the width of the rectangle.
okay.
So that is important to put in there. It also kind of acts as the other bookend of where our integral is. you don't need parentheses. You have the integral symbol and you have your dx, and everything inside is inside the integral.
Okay.
Let's do one more. Okay, let's do one more. We have here the derivative of what would equal, and I'm going to rewrite this as x to the negative 1/2. Okay? So you're thinking about x to the 1/2. The derivative of x to the 1/2 is 1/2 x to the negative 1/2. So what'd you say?
You said it's 2x to the half.
Yeah. Multiply by a 2 to get rid of that half, and we get what we're looking for, x to the negative 1/2. So we would then say the integral of radical x dx
It's 2 radical.
is, or wait, sorry, not 1 over radical x is 2 radical x. Okay?
Couldn't it be also ln radical x?
That would be if it were just a 1 over x.
Oh,
Actually, and that's good intuition there. The derivative of ln of x was 1 over x, so the integral of 1 over x is ln of x. That's good. Okay, we'll actually learn that rule later, so that's really good. But guys, that's the kind of thing that you can do with these. If you know the derivative of something, then the integral of that will take you back to your original. Okay? Now, here's the one question though, and that is, are those the only functions that could be the antiderivative?
You could
Okay.
also do like plus c.
Okay. The derivative, this is why these are not exactly inverse ideas or inverse operations.
This would be a constant.
Because the derivative of a constant is
0.
0, okay? So let's think about our x to the 4th over 4. That's kind of an easy one. Okay, x to the 4th over 4, okay, the original function, it has a quadruple root at 0. And it's stretched way out, so it goes like this, okay? Here's x to the 4th over 4. Okay? Now, I know that the derivative of x to the 4th over 4 will give me x cubed, right?
Yes.
However, if I took that, and let's say I made it like this. Exactly the same, but I raised it up 3. So now that's x to the 4th over 4 plus 3. The derivative of that would also be x cubed. Okay? Or if I took this and I just did something like this, okay, here's a minus 1. Try to draw this decently. Here's x to the 4th over 4 minus 1. Okay? All of these, the derivative is x cubed. Therefore, if you add any constant, okay, you can add any constant and the derivative stays the same. Now what that means here, guys, is that a function will have more than one antiderivative. And the way we denote that is up here on these three. That actually wasn't the entire answer. Okay? Each one of these, the antiderivative would actually be x to the 4th over 4 plus c. We just use c for a constant.
Huge.
Okay? here, the antiderivative of e to the 2x dx is 1/2 e to the 2x plus any constant. The integral of 1 over radical x dx is 2 radical x plus any constant.
So we have to write plus c for it.
Okay, so you've got to write plus c. Now, what we'll find later on is if we find definite integrals where we're evaluating, the plus c doesn't matter. That's what's kind of cool. Okay? So we'll work with this plus c in a couple of different ways, but that's the concept of getting the antiderivative. Alright, so what we want to do here in our practice for this lesson is I want you to try to think through some of these intuitively. I don't want you to look up rules. Okay? Think through these. We've already done, we already did an x cubed, which isn't on here. We did already do x to the negative half. Okay? But I want you to try to work through these and intuitively come up with a rule on your own. Okay? And then on these ones, it's kind of the same thing. The antiderivative of e to a power, okay? And notice here, it's like predict a general rule for the antiderivative of e to the kx, where k is some function. Notice here, the exponent's still linear, okay? The rule that you're going to come up with, hopefully, won't work if it's like x squared or something like that. But as long as it's something x, it will, okay? And then we take it up another step here. Take the derivative of this and use that to find the antiderivative of this. Okay? So, just as an example here, for part A, so if I take the derivative of x cubed plus x squared, okay, the derivative of x cubed plus x squared, 3x squared plus 2x, okay? So, let's think about if I want the antiderivative of 6x squared plus 4x, okay? Can I factor out a 2?
Can.
Alright, let's do that. And actually, one thing with integrals, because they're limits and sums, remember you can take a constant multiple out of a limit or out of a sum. So that means we can take it out of an integral as well. So I could take the 2 outside the integral.
You just put it outside of the square root, okay.
Yep. 2 times the integral of 3x squared plus 2x dx.
And then it's just
What's the integral of 3x squared plus 2x?
x cubed plus x squared.
X cubed plus x squared plus c, okay?
That goes on the inside of the parentheses?
It actually doesn't matter. I was going to say that. So we have 2x cubed plus 2x squared, and you don't need to write plus 2c because c can be anything. So you just keep the plus c at the end.
Okay.
Okay? So that's how you could handle those. But that, again, I'm trying to get you used to this whole concept of the inverse relationship here. And the better you understand that now, the easier this whole unit's going to be for you. Okay?
Would it matter
I'd
if
like it to be
someone
easy.
did write 2C?
No. I mean, if you write 2c, it's still a constant, you know.
Right, because
So.
it's c, it's
Yeah, because it's a random constant anyways, it equals any real number. 2 times any real number is still any real number, so. Okay?